Now let us talk about the graphical representation of this complex number. Of course, as we had seen in our previous lecture, we generally represent our complex number in two axes, the y1 which we call as the imaginary axis and one is the real axis. Now what is this plane known as? This is of course not our xy plane. So this plane is what we call as the Argand plane. So this is my Argand plane. Now here again the point that I am representing is a plus iota b, and this is basically z. Z is equal to a plus iota b. Here a is my real part. So if I try to project this value on my real axis, this length would come out to be a. And if I project it on the imaginary axis, this length here, this point would be b. This point would basically be 0 comma b. This point is a comma 0. So this length here is my b. That is why this entire length, which we call as the modulus, this is basically the hypotenuse of this right angle triangle that we are getting. So my modulus of z becomes root under a square plus b square, and my theta becomes tan inverse of b by a. Now what is this theta that I'm getting? This theta is the angle of my complex number that it is making with the real axis. Now this angle is generally taken in anti-clockwise direction. So remember, this theta is taken in anti-clockwise direction. And what do we call this theta? This theta is known as argument. This z here is known as modulus, and this theta is known as my argument. Now again, there is a separate lecture based on argument where we will be studying more detailed analysis of what theta is and how we can calculate it and how it varies based on the quadrants of our Argand plane. So there we'll look at these things in more detail. For the time being, just remember theta is equals to tan inverse b by a. Let us look at this question now. Let alpha and beta be the roots of this equation, then the value of alpha to the power 8 plus beta to the power 8. So if I look at this question, this function that has been given to us, x square can be written as 1 minus 2 iota, and for this equation alpha and beta are the roots. That means alpha and beta would satisfy this equation. That means alpha square would be equal to beta square would be equal to 1 minus 2 iota. That means first relation from this equation regarding alpha and beta that we got is that alpha and beta are same. Sorry, alpha square and beta square are same. Alpha and beta are not same. Alpha square and beta square are same. So if in my modulus I have alpha to the power 8 plus beta to the power 8, so can't I write this alpha to the power 8 be equal to beta to the power 8? Because if alpha square is equals to beta square, and if I square both the sides twice, then it would simply become alpha to the power 8 and beta to the power 8, right? So this would become basically 2 alpha to the power 8. So basically we have to find out our value of 2 alpha to the power 8. Now we know that alpha square is equals to 1 minus 2 iota. What if I take its modulus? So my modulus of alpha square would be 1 minus 2 iota's modulus. And what is the modulus of 1 minus 2 iota? It is root under 1 plus 4, which is root 5. Now what if I try to convert this in terms of alpha square? Then I would be able to find out my answer. So this can also be written as 2, since it is a constant I can take it outside. Alpha to the power 8 can be written as alpha square to the power 4. So basically this becomes 2 into root 5 to the power 4, and root 5 to the power 4 is nothing but 25. 25 into 2 becomes 50. This is my answer. So a very easy question. The only thing is that you had to replace your alpha beta in the equation. From there you would have found out that alpha square is equals to beta square, and once you got that, solving the modulus is a piece of cake for us. So now let's talk about conjugate of our complex number. Of course, we've already studied this. If z is equals to x plus y, then what would its conjugate be? z bar would be x minus iota y. And if I was to represent them in the Argand plane, it can be represented in this format. The x is same for both these complex numbers z and z bar. However, my y is ranging. It is y for the first case and minus y for the second case. So you must understand this type of graph. Now one thing that you must remember is that when can my z be equal to my z bar? This is possible if z is purely real number. Let's say if z is a purely real number, that means I wouldn't have any imaginary part. And if imaginary part is eliminated from both these cases, of course z is equals to x and z bar would also be equals to x. So that is how I get my z is equals to z bar. And now let's say if my z is equals to minus z bar, that means what I can say is this is possible if z is purely imaginary. So if my z is purely imaginary, that means I can remove the x part, then my z would be equal to iota y and my z bar would be minus iota y. So that means my z is basically equals to minus of z bar. So keep these points in mind. If these two equations now, if I was to, let's say, represent them in, let's say, a standard format, then what I can write about this equation is z minus z bar would be equal to 0. And for this equation, I can write this equation as z plus z bar would be equal to 0. So keep this thing in mind. Generally, when we solve questions, you can use these functions to solve your questions, because sometimes in question they are going to give you this point that your z is purely imaginary or purely real. One example that we are going to be looking at after this concept would be based on this concept only, that z plus z bar would be equal to 0. From there you would have to calculate the unknown variables that have been given to you. So keep these equations in mind. Now there are a few properties, of course, that you need to keep in mind. If z plus minus z2 is equals to z1 bar plus minus z2 bar, z1 z2 whole bar can simply be written as z1 bar z2 bar. Again, the properties that we had for modulus can same be repeated here. Again, as for modulus we had the division properties, similarly that was repeated here. Now real part of z plus z bar by 2. Sorry, real part of z is z plus z bar by 2. And imaginary part of z can be written as z minus z bar by 2 iota. Now let's say if my z is x plus iota y and my z bar is x minus iota y, then z plus z bar would be 2 times of real part of z, and z minus z bar would be 2 times of iota into imaginary part of z. So keep this thing in mind. And if we take the double conjugate of any complex number, it would simply become the original complex number. If we take the modulus of z, it would be equal to the modulus of its conjugate as well. Z into z bar would always give us modulus z whole square. Again, these are properties that are repetitive again and again, so that you start remembering all these properties and it gets into your head. Now let's look at this question. Now the property that we just learned about purely imaginary and purely real number, that is going to be used in this question. The set of all alpha belongs to R, for which W is equals to 1 plus 1 minus 8 alpha Z upon 1 minus Z is a purely imaginary number. So we know that W is a purely imaginary number. So if W is a purely imaginary number, then what I can say is W plus W bar would be equal to 0, as we had studied the property here. If Z is a purely imaginary number, then Z plus Z bar is equals to 0. So W plus W bar would be equal to 0. And if I try to find out the conjugate of W, what would it simply be? It would be 1 minus Z and 1 minus 8 alpha Z bar upon 1 plus Z bar. So Now let me use this function with the w that has been given to me. I can write it as 1 plus 1 minus 8 alpha into z, and below I have 1 minus z. What would its conjugate become? Again, if you carefully look at this equation, of course this sign and this sign I'm not going to change in the conjugate. I'm simply going to put x bar in my conjugate, because these signs cannot be changed, because I'm considering this whole to be a purely imaginary number. This entire thing cannot be taken as conjugate. So this would simply become 1 plus 1 minus 8 alpha into z bar upon 1 minus z bar. This is equals to 0. Now what I'll do is I'll take LCM and cross multiply. So this would become 1 plus 1 minus 8 alpha z into 1 minus z bar, plus here I would have 1 plus 1 minus 8 alpha z bar into 1 minus z, and below I'm going to have 1 minus z plus z bar. Sorry, this would become 2 because z into z bar. Now how do I come to this conclusion? 1 minus z into 1 minus z bar. How can I write this down? This would become 1 minus z bar plus z into z bar, and using the property z into z bar is equals to modulus z whole square. So this would become modulus z whole square, where in the question they've given us that modulus z is equals to 1. So if modulus z is equals to 1, so this would become 2, and I take minus common, so this would become z plus z bar. This is equals to 0. Now based on this equation, one thing that you can say is that z plus z bar cannot be equal to 2. This is the first thing that you can say, because if it becomes equals to 2, my entire equation would become undefined, right? I would have a 0 in my denominator, which makes the entire value go up till infinity. So this cannot be the case. Now if I've applied this case that z plus z bar cannot be equal to 2, then now I can cross multiply it with the 0. So if I cross multiply it, this would simply go away, and now I would be left with only the numerator. Now let me try to simplify the numerator. What would I get? 1 minus z bar plus 1 minus 8 alpha into z minus 1 minus 8 alpha. Of course I would have a z into z bar here, which would become modulus z square, which is simply just 1, plus now multiplying the other one, I would have a 1 here minus z plus 1 minus 8 alpha times of z bar, and then I would have a minus 1 minus 8 alpha is equals to 0. So this is what I'm getting. Now if I try to simplify this equation more further, I would have 2 minus z bar plus 1 minus 8 alpha. If I take it as common, I would have z plus z bar here, and here I would have minus 2 times of 1 minus 8 alpha. This is equals to 0. So from here, now what I'll do is I'll take I can take z plus z bar common. So I can write this equation first of all in this way: z plus z bar plus 1 minus 8 alpha z plus z bar minus 2 times of 1 minus 8 alpha is equals to 0. So this can basically be written as this 2 and this 2. This 1 here would be cancelled out because here I would have minus 2. Now here I would also have a 16 alpha. So what I'll do is I'll take this 16 alpha to the other side. So here I would be left with z plus z bar. I'll take it common. So here I would have minus 1 plus 1 minus 8 alpha. This value is equals to minus 16 alpha. So from here what do we get? Z plus z bar into 8 alpha is equals to 16 alpha. So this is the equation that we've gotten now. Now I can cancel alpha provided that I have to assume that alpha is equals to 0. Now what are the ways or what are the cases in which this equation would become satisfied? This equation would become true. Firstly is that z plus z bar, if it becomes equals to 2, that means this equation would be satisfied. I would have 2 into 8 alpha, which would make it to 16 alpha, right? However, here we had assumed that z plus z bar cannot be equal to 2, because if it becomes equal to 2, my entire equation would become undefined. So this cannot be the case. So from here, the only answer that we get is that alpha should be equal to 0. If alpha is 0, then only this entire equation would be satisfied. So we get our alpha as 0. And what was asked to us in the question? The set of all alpha for which all of these satisfy. So there's just one value of alpha that will satisfy this entire equation, and that is 0. Now, of course, if you have any doubt regarding the answer that you've just gotten, you can always put it in the main equation that was given in the question and check whether it is coming out to be true or not. Let's see, if I put alpha as 0 in this equation, what would I have? I would have 1 plus z upon 1 minus z. And if I look at this equation carefully, this is going to be nothing but, if I multiply it with its conjugate, of course I'm going to get a purely imaginary number, right? Where I can assume that my real part is not equal to 1. So of course this value of alpha, which is 0, satisfies this equation. That means the value that I just found out is correct. So this is how you solve questions which are related to conjugate. Just remember one thing, whenever you write down the conjugate of an entire equation, you do not use minus signs or you do not change the signs of the entire equation. Simply you can put bar on the z, the complex number that you've gotten, and that would simply become your w bar. Let's look at one more question. Z is equals to 2 plus 3 iota, then z to the power 5 plus z bar to the power 5 is. So in this equation, first and foremost thing, what we are going to do is, let us write down what our z bar is going to be. 2 minus 3 iota. Now simply what we'll do is we'll put it in the equation that we need to find out. So we need to find out the value of 2 plus 3 iota to the power 5 plus 2 minus 3 iota to the power 5. Now what I'll do is I'll use binomial expansion to expand these two functions. Now if I expand these two functions, I hope you all remember in binomial theorem we had studied, if I have x minus y to the power n plus x plus y to the power n, then what does it become? It becomes 2 times of nc0 x to the power n plus nc2 x to the power n minus 2 y to the power 2 plus, and this goes on up till the end. We are going to have all the even bases in my combination, right? Because all my odd cases would be cancelled out, because in one of the expansions I have minus y and in one of the expansions I have plus y. So all my odd terms would be cancelled out. So here also similarly we would have 2 times of, here I would have 5c0 2 to the power 5 plus 5c2 2 to the power 3 3 iota to the power 2 plus 5c4 2 to the power 1 and 3 iota to the power 4. So this would be my summation of this entire term. So now I'll simply find out the value. What is it coming out to be? 5c0 is 1, 2 to the power 5. What is 2 to the power 5? 2 2s are 4, 4 2s are 8, 8 2s are 16, 16 2s are 32. Plus, what is the value of 5c2? My 5c2 can be written as 5 into 4 by 2. So this would become 5 2s are 10. 10 times of 8 into 3 iota square. Iota square is basically minus 1. So this plus can be removed and written as minus here, and 3 square would become 9 plus 5c4. 5c4 can be written as 5c1. So it would become 5 into 2 into 3 3s are 9, 9 9s are 81, and I to the power 4 is nothing but 1. So now if we try to calculate this entire term, what are we going to get? This would become 122, and we have a 2 multiplied outside as well, so this would become 244. This is our answer. So again, a very simple question. The only thing is that a little bit of concepts of binomial theorem was used in this question that you had to remember from studying that chapter. Apart from that, if you look at the concepts that were used of complex numbers, there was nothing, right? You simply had to replace the value of conjugate and the original value in the equation that was asked, and you would have found your answer. And this was a question that was asked in one of the previous year JEE Mains. So you can understand the level of questions they are asking. They are very easy.